The first speaker is Professor Norberto Scoccola from Buenos Aires. Please, Norberto, the mic with you.
Okay, so I would like to ask Anna and Jorge for the opportunity of being here and presenting my work. What I will discuss today is the anomalous pi-zero decay in the strong magnetic field using the non-General model. So I will start with a brief motivation, and then I will describe how to understand or calculate the properties of the pions and pion coupling constants in the non-General model of finite magnetic field. And these are the ingredients that I will need to calculate the anomalous pion decay. And then I will end with some summary and conclusion. And this is work done in collaboration with Max Coppola and Daniel Gomendum from Argentina too. So I think I don't have to say much about this. There has been a lot of interest in the last couple of decades to understand how strong matter is affected by this intense magnetic fields. And the motivation is that such magnetic fields can exist in the interiors of some compact stars, also in heavy ion collisions, and also at the early universe. So because of this, there has been also a lot of interest in understand how hadronic properties are modified by the presence of the magnetic field. For example, meson masses have been, meson masses have been studied, and finite magnetic field and temperature using different models, and also lattice QCD. And in particular, for what I'm going to say, it is important to recall that neutral pion mass is found to decrease with the magnetic field, both using effective models, as I said, and also using lattice QCD calculations. There have been also calculations of the width decays of the charged pions. Again, these were analyzed using lattice QCD calculation and non-General models, and the result of those analyses that the width is enhanced by the magnetic field. So the topic of my talk is how pi-0 to 2 gamma, this anomalous decay, is affected by the magnetic field. And I will do that using the non-General model, as I said, and I will recall you that at b equal to 0, the width is basically given by the Vesumino Witten term. So in a way, it will give us some way to understand how this anomalous decay is related with the Vesumino Witten action in the presence of the magnetic field. So I will give some details of the model I will use. This is the non-General model, which is gauged in the sense that the magnetic field or the external electromagnetic field is included through this covariant derivative, and the electromagnetic field I will divide in two pieces. This is the classical part, which is basically given by the external magnetic field, and this is the photon field, which are kind of fluctuations around this background. As I said, I mean, for the classical external field, I will use a constant magnetic field. For example, in Landau gauge, this field is given in this way. And I will show later on, in fact, I don't need to use any particular gauge in my calculation, so I will show that the calculation is gauge invariant, actually. So this action, which is written in terms of fermion fields, can be bosonized introducing the meson fields. And this action here is completely equivalent to this one. But here now the relevant fields are the sigma field and the pion field. And this operator here has a delta function, is local and in space, if you like, and contains the covariant derivative and the meson fields. So what I will do next is to use the mean field approximation. So I will expand around mean field values of the meson field. So I will assume that sigma field has a non-vanishing mean field, while the pi 0 and pi plus, pi minus do not have such mean field value. So I will separate a mean field part and fluctuations around this mean field. So the mean field part here is given by this operator, where here I have included external magnetic field. So this means that at mean field level, I will have to solve, for example, the equation for the mass, so the gap equation in the presence of the external magnetic field. So this mass here is the sum of the current quark mass plus the mean field component of the sigma field. And the fluctuations now contains the photon field and the fluctuations of the sigma and the pion. So what I would do is to expand the bosonic action in powers, if you like, of delta x. So we have some mean field part, quadratic, cubic, etc. So at the level of mean field, this is what I have. And here is the quark propagator, and of course this is the quark propagator now in the presence of the external magnetic field. So for that purpose, I will use the Schwinger propagator, as it was already given in some previous talk, which contains a phase here, which is the Schwinger phase, and a part which is translation invariant, and therefore I can Fourier transform. This part is given by this expression here. So if you plug this in this expression here, you get the bosonic action at mean field level, and then you take the derivative with respect to the mass, and then you get an equation for the effective mass, quark mass, in the presence of the magnetic field. So next, I will go to the quadratic fluctuations and to calculate the pion mass. In principle, you can calculate the pi plus, pi minus, and pi 0. So here, I will concentrate only in the pi 0. For the pi 0 case, since the quarks in the loops have the same flavor, the Schwinger phase is cancelled, and therefore I can Fourier transform everything, because everything is invariant under transformations. So I get this form for the quadratic part corresponding to the pi 0. So here you have the 2-point function here, which is given basically by this trace of the quark propagators. So again, you plug the expression given in the previous transparency, and then you get an explicit form for this pi 0. And then if you look for the poles of this gives you the equation for the pion mass. Okay? And if you take the derivative of this with respect to the q square parallel, and evaluate it at pi equal to 0, you get the coupling constant. So in principle, you have already the pion mass, the coupling constant, and the quark mass. So now you can start calculating the diagrams that you are interested in. So the pi 0 decays into 2 gammas is given by this expression here. I don't know. It seems to me that this is not working. Anyway, this is the upper part of the transparency. And then the contribution to the amplitude is given by these two diagrams. And using the usual Feynman rules, you can see that the analytic expression of these two diagrams is given in this box here, while the first term corresponds to diagram, and this one to this one. And the implicit form of this amplitude is given in the last line, which is in a way similar to the one that you have b equal to 0, except for the fact that now the coupling constant of the pion should be calculated as finite b, and the propagators are the propagators as finite magnetic field. Now, if you now recall the form of the quark propagators, you remember there was a part depending on the Schwinger phases, and this is taken outside of the integral of the momentum, and then you have the integral of the momentum of the three quarks and the three propagators. Now, since all the external particles in the triangle are neutral, you can show that the sum of these three Schwinger phases is gauge invariant. Okay, and if I choose the magnetic field around the third axis is given by that form there. So it's gauge invariant, but contains the coordinates. So in a way, it's still completely translation invariant. Now you have to notice that the two diagrams are connected by charge conjugation. So you can sum up over. You can sum the two diagrams, and you get this final expression here, where this epsilon here means that you take the charge in y case positive or negative, depending on epsilon. There is a sum over epsilon here. Okay, and this factor g contains the integrals, all the integrals over the coordinates. And this is given in the next transparency. Oops. Here, which is kind of complicated integral because you have to integrate over three different coordinates, and in addition, you don't only have the exponential that you always have, but you also have the Schwinger phase contribution. But anyway, this integral can be done exactly, and you get this expression where there is a delta of the total momentum of the external particles, but then you notice at each vertex there is a delta for the parallel momentum, but it's not the delta for the perpendicular momentum. And this is due, of course, to the Schwinger phase. Anyway, since there is a delta over the total momentum, you can take away this, and then you can define these R functions where I took away the delta, the total delta of momentum conservation, and the polarization of the photons. So you have to calculate these R functions, which is the subindex implies the flavor. And this is an integral over three momentum, so this three-fourths momentum, so there are a lot of integrals there. And in addition, you have to take the traces, and you have to remember that these propagators are not so simple as the one you have in the absolute magnetic field, so you have all different components with several gamma modes. So this is quite complicated calculation. And in addition, in the integrals, you have to take into account the Schwinger phase. Anyway, after some lot of work, this integral can be done. And provided, well, you get a quite simple result, if you like, provided I stay in the pion frame, in pion rest frame, because after all, I'm calculated the pi zero decay. And I assume that the photons satisfy that their momentum square is equal to 0. Okay? So after a long calculation, you can show this R functions, as I said, is a trace of a lot of Dirac matrices and integrals and so on, it gets a quite simple form, which is given up there. And this function, this integral IF is given by this here, where T1, T3, etc. are tangents of the of the magnetic field, and this taus, which are the what's called the tau function that appear in each integral here. So sigma is I tau, basically. So it's a proper time parameter, okay? So you are still left with the integrals over proper times. You have the 3 proper time because you have 1 proper time associated with each propagator. So we have still performed the sum over the photon polarizations, and this can be done, and this is the result. So in the end, you get that the width is given by this expression, where the coupling constant by 0 to 2 gamma is given by this. This omega here is cos of the angle between the magnetic field so you can make this change in the proper times parameters, and you finally get. The problem is that, can you hear? It's red. It's green, I'm sorry. Should I use it? Now, can you hear me? Okay, I will talk like this. So these integrals, after you make this replacement in the proper time parameters, is given by this. So this is the final formula. So in principle, once you have m of b, pi of b, and qq of b, everything calculated in the number generation model, you can calculate the width. So, but before giving you some numerical results, I will see that I can take, I'm sorry, the chiral limit, meaning that I can calculate this coupling constant in the chiral limit, meaning that I will take m pi equal to 0 here, okay? And this I will show in the next transparency. So this is the same integral. I put this upper index chiral to indicate that I'm taking m pi equal to 0. And this integral is a triple integral, as you see, and it has a lot of tangents of the magnetic field and everything. However, surprisingly, perhaps, this integral can be done analytically. And the result of all this integral is given here, is 1 over 2m squared. And if you now replace in the expression for the coupling constant, you get that the coupling constant is nc divided by 12 pi squared, coupling constant pi qq divided by m. And now if you use the Goldberg-Treiman relation, which you know it is valid in the chiral limit within the Namoch-Rosino model, you get that the coupling constant is nc divided by 12 f pi of b. And, well, perhaps some people suspected that this must happen because this is the result of a Besomino anomalous term. So in the end, this is the final result at leading order n pi. Is the same result as b equal to 0, except for n pi has to be replaced by n pi of b, and f pi has to be replaced by f pi of b. So, of course, this is in leading order in n pi. Okay? So it's nice that you recover this result. So in a way, okay? So numbers. So I use standard numbers for the number Chirally model, and I will consider two cases. The case in which the coupling constant is constant, and the case in which the coupling constant depends on the magnetic field, which is the thing that you have to do in order to reproduce inverse magnetic catalysis at finite MT. So this is the comparison of the behavior of the condensate as a function of B. These blue dots are lattice QCD, and this is for constant G, and this is for G of B. G of B is a little worse, but however, it's fine. And this is a comparison of n pi of B divided by n pi of 0. This is if you use G constant, and this is if you use coupling constant dependent of B. So you get a very reasonable description of the pion mass and the condensate. So and now this is the result for the pi 0 to 2 gamma width. Using these parameters at b equal to 0, you reproduce very well the empirical result. And you see that what we find is the width decreases with the magnetic field. And this is for G of B, pardon, this is for G constant, and this is for G of B. So for G of B, I mean, they are similar, but however, in the case of G of B, the decrease is a bit larger. So in order to understand what's going on and why this decreases, it's interesting to compare this result with the result at leading order n pi. And this is here. This is the leading order, and this is the full result. And as you see at the beginning, there is some small discrepancy of about 4%. But however, as B increases, they are basically one on top of the other. So the difference between leading order and full is very small, or basically vanishes as you increases with magnetic field. So then, since this is true, I can try to understand why this decreases using the expression, the simple expression I obtained to leading order. And so if you take the leading order and you take the width of dependent on B divided by the width divided at B equal to 0, you get this is the ratio of n pi cube multiplied by the ratio of f pi cube. Now, you know that n pi 0 decreases with B, so this number decreases with B. And on the other hand, using the Gelman-Ox-Renner relation that relates f pi of B with the condensate, which is also valid in the number Chirally leading order, since you know that due to magnetic catalysis, this increases and this decreases, so you expect f pi to increase. So in a way, this ratio is decreasing, and this ratio is also decreasing. And this is the reason why the full width decreases. You might wonder which of two defects is larger. This is shown in this last transparency. So where I plotted the ratio of the masses cube as a function of the magnetic field, and this is the ratio of f pi as a function square as a function of the magnetic field. So this is for G constant, and this is for G of B. And you see that in both cases, well, perhaps more clearly here, the effect is, both effects are similar. So the total decrease is, say, half due to the decrease of m pi and half due to the increase of f pi. And you can also understand through this figure why the G of G0, the decrease is a bit smaller than in this case. And this is because for G constant, pi 0 remains almost constant, while in this case, it goes down a bit more. Okay? So I come to summary and conclusions. We considered anomalous pi 0 decay in the presence of the strong magnetic field using a SU2 model. We have found that the full expression for the width reduces to the leading order in pi to a simple expression, and this simple expression is consistent with the Vesuvino anomalous action. The width is found to decrease with B, and the decrease can be explained in terms of a decrease of m pi and the increase of f pi. Finally, I would like to mention that in this calculation, we have made some assumptions. For example, we have neglected effects due to the pi 0 gamma mixing. We know that in reality, the pi 0 is not a fully pi 0, but is mixed with the gamma. So this might give some changes in our calculation. And the other thing that we know that if we include loop corrections to the photopropagator, then we'll get dielectric constant, which are different from 1. And this means that k squared, so the momentum square of the photon is no longer 0. So this will also give some contribution. But of course, we are leaving this for future work. So thank you very much.
Questions?
Of course.
Of course.
No lowest Landau level approximation here.
Okay. No, I actually wanted to go beyond the lowest Landau level approximation. The G, where do you get it from? The G behavior with B?
Some of your papers.
So the question is, can you compute it in the model itself? Is there a way
No, this is something
there is nothing to do with it?
No,
okay.
This is external to the model. I mean, what you do usually is to calculate the critical temperature and try to find some function of G of B that fits the decrease of T of the critical temperature found in lattice QCD. So this is an external thing.
And
so
second,
something that you fit from other sources.
good. But the masses you can get from the model,
Oh yeah, of course.
capital M and small m. Okay.
Of course, maybe. As I said here, all the parameters that enter here and here and here are basically the quark mass, m pi, and the coupling constant. And all this I calculated within the model.
Yeah. And last, the transversality of your vertex, because see, you have pi 0 going to gamma gamma.
Yeah.
It should be transverse when you dot with the momenta of the photons. I didn't see it in your formula. Can you show again your expression? Your tensor structure, yes. That R, I guess. No, further up. Further down, that is.
Down?
Well, advancing
one
there.
more. Here. Well, I didn't check that. But it should, I mean, because if I take the Cara limit, I recover the Vesuvino Witten result, so it should be.
Okay.
But I didn't. I mean, I didn't try it explicitly.
Thank you, Norberto. It's a very nice calculation. Can you go to the slide where you define the G of B? This may be just a small comment. Can you go to the slide, please, where you define the G of B, the capital G of B with the condensate and so on?
No, I'm sorry, I'm going the other way around.
Yeah, so did I get it right on the left plot? If you use a constant G, then you are right on top of the lattice results, and if you use the magnetic field tuned GB, then you go away from it?
Yeah.
Why is it like that?
Why here I get just on top of the, well, I don't know. I mean, what I can say is that this G of B is not fitted here.
It's fitted to the finite T thing. But I had the impression, I thought I remembered that it also improves the zero temperature behavior of the condensate. That was how I remembered it was. So it's like this, really? Good to know.
No. The G of B is fixed to reproduce. I mean, this is not my work, actually. I mean, this is work by several people, including Sarah in the audience. Maybe they can give more.
Just the function that fit the lattice results at zero temperature and find the magnetic field. Okay, the constant one is to be the right curve, right? The G of B is above the point. Okay, yeah, this is the point. The legend is changed, the lines. Okay, just the colors of the legends is changed. This is confused, girl. The G of B is above the points.
No. No.
No, why?
It's not fitted here. Huh? No, this is correct for sure. I mean, if you used a G of B that reproduces inverse magnetic catalysis, the agreement is not so good. But it's not so bad either. I mean, well, this is kind of.
No, but there are lots of results for zero temperature, right?
This is
we
kind
fit
of
that
accident.
one.
Wait. This is kind of accident. This is
Yeah, we fit that one with a couple.
If I change a bit the parameters, you move a bit away. So there is a band, if you like, and the band is more or less center in the lattice QCD points, but there's some spread. So I took one. I mean, how to say? I shouldn't give too much importance to the fact that they are just on top of the. The only thing I want to show with this is that it reproduces the trend, not that they are just on top. Okay. Maybe I should choose another set of parameters that is a bit away from the lattice point, so it's not to give it the impression that this is perfect. I mean, okay. Yeah.
Okay, we're running out of time.
By no means I mean that this is perfect.
Okay, we're running out of time. Please, thanks, Norberto, again.
Tá ligado já? Como é que é o negócio aqui do controle? Can you hear me? Okay, it's nice. Tá.
So the next speaker is William Tavares. He's talk about Chirally imbalanced medium in a four-fermion interaction model beyond the large N approximation.
So, good afternoon. First, I want to thank the organizers the opportunity to present part of my work. Okay, today I will try to revisit some interesting results with the phase diagrams, with the chiral phase transition, with the chirochemical potential μ5, okay? Here I will be using the NGL model in the mean field approximation and the beyond mean field approximation. Well, this work has these collaborators here, Rodney Ramos, Marcos Beng, Ricardo Farias, Diana Duarte, and André Gonçalves. So, I think yesterday we had very nice talks about the environments with a chiral imbalance. So here, basically, I will just set these three basic ideas that the chiral magnetic effect, that maybe is the most important physical system we do expect that the chiral imbalance occurs. And also high temperature QGP, and maybe very high, maybe compact objects, okay? Okay, here I will try to revisit some results from like 10 years ago that we had these Dyson-Schwinger equations with tells us that the pseudocritical chiral temperature for the transition temperature increases with the chiral chemical potential. Also, and when include the quark chemical potential in the right plot, okay? So we have this increasing behavior. This is the expectation idea. But the lattice QCD guys tells us that this is indeed the behavior we can expect when we look also to the lattice QCD and the two-color QCD in the right plot. And then it's natural that people from effective models try to do the same thing, to calculate these phase diagrams, because effective models usually are very good at environments to calculate several quantities, also at finite chemical potential, because we can control these quantities in these phase diagrams. And what we have here is this result on the left, that we can see the behavior very different from the Dyson-Schwinger equations and lattice QCD, which we see the decreased behavior of the pseudocritical temperature, and also we have a critical endpoint and the first order line transition. And until these days, 2024, we have the same behavior, this decreasing behavior of the pseudocritical temperature, and several other works. So it seems that this idea of the behavior of the phase diagram with the chiral chemical potential is not exactly well understood or well understood by the community, okay? So what we'll try to do here is to look what we have in the two-flavor NGL model here. Here we have the basic Lagrangian of this model. We have the free Lagrangian part, and we include the contribution for the chiral chemical potential, and we have the interaction channels, okay? This model is not normalizable, so we have to find a way to regularize the physical quantities we want to see, and if you like to see more details, we have this very good reference. Well, the first thing I will try to see here is what happens at the mean field approximation, which is the same thing to say that large NC approximation for this model. Here we have to compute that diagram, okay? And when we do that, we have this basic free energy of the model. The first term is basically the mean field term that we call the mean field term. And the second term is a divergent contribution, so we can regulate with the three-dimensional cutoff. And the last contribution is a thermal contribution that depends of the temperature and the chemical potential. Here we have zero chiral chemical potential. And the idea here is that we regulate the vacuum contribution. In principle, you can regulate the thermal contribution, but if you do that, maybe you will find some violations of causality in the theory. So I will put the thermal cutoff to infinity, okay? So if you wish to include the chirochemical potential, you have to solve the functional generator of this model in the mean field approximation. And after the calculation, we will find the quark energy relation dispersion, okay? That depends now on the chirochemical potential. But we can just, to simplify the notation and the calculations here, we just do that displacement. Now the integrations depends on the summation on spins, and we have to change the quark dispersion relation. Here we have also the three quantities, the three SAM contributions, okay? And in the same way we do for zero chirochemical potential, we have to regulate. And now is the moment that the things get nice to understand what is happening with the phase diagram in these effective models. In this left side, we have the basic idea. We have just to regulate the vacuum contribution, and we put a three-dimensional cutoff there, so that's it. And the problem here, the apparent problem here, is that we have some kind of entanglement between the vacuum contributions and the chirochemical potential, okay? In the right side, we have an idea to regulate these integrations, which we call here the medium separation scheme. It's a very nice trick to calculate these contributions, okay? And Ricardo Farias, Diana Duarte, Gastão Klein, and Rudney calculate this very nice trick in 2016, okay? And you can indeed separate the vacuum contributions from the mu5 contributions. The basic idea here is that we can calculate the integrand from the free energy using just a trick, using the derivative of the effective quark masses. Then we have the result in the right side on equation 3. Then this integration function, we can separate the terms with, we can see in equation 4. Then we apply 3 times the same trick, and we find equation 5. Here, these contributions that has this 0 index are just the quark dispersion relation with the effective quark masses fixed to the vacuum value, okay? And the nice idea here is that when you separate these contributions, the first term is quadratically divergent, so you can just regulate with the cutoff. The second and the third are also divergent, okay? And the fourth term is finite, so just for the fourth term, you have to, you can integrate until the infinity. Well, here is the result. When we apply the medium separation scheme, we can see that the pseudocritical temperature indeed increases with the chirochemical potential, okay? If we apply the traditional regularization scheme, which is just including the cutoff on the full integrations, we have this decreasing behavior with a critical endpoint. Even the effective quark masses changes with the regularization. If you see, when we use the traditional regularization scheme, the masses goes up and then goes down at some point. So this was the idea of the medium separation scheme. But now we want to see what happens in this environment when we apply beyond mean field approximations. The idea here is to look to the optimized perturbation theory. Marcos Bengue-Pinto, Rudney Ramos, and Jean-Louis calculated this optimized perturbation theory at order delta in the 2-flavor NGL model. And here I showed just 2 examples of the difference that we can find if you apply this beyond mean field approximation. We can have these displacements, these little shifts between when we look to the left plot, when we have the 0 temperature equation of state, and on the right we have also equation of state, and we have some shift for lower values of the temperature, okay? So now we wish to see what happens when we have the mu5 in the game. So the basic idea of the optimized perturbation theory is to use a new Lagrangian, which is some kind of interpolation between the free Dirac Lagrangian with the full Lagrangian. We will use this delta term, okay? So we have the free Lagrangian, the original Lagrangian in the mean field approximation. Then we have the Lagrangian that interpolates between these two quantities. If we put delta equals to 1, we have just the original Lagrangian, and delta equals to 0, we have the free Lagrangian. Then we understand that this delta term can be a very small number, and we do a series expansion in this theory, okay? For dimensional balance, we have to include a new mass term, and this new mass term has to be has to not change since the physics we want to see. So we include this new condition that we call principle of minimal sensitivity. Then, to do things work, here we apply the Lagrangian in the mean field approximation, then the Lagrangian interpolated with the optimized perturbation theory at order delta, and we redefine the mass term with this equation 10. When we look to the effective potential or the free energy of this theory, we have to calculate these three quantities, okay? I will not bother you with the calculations here. I will just put the final result. So the first contribution will give us the basic free energy of the mean field approximation. And the other two quantities for each channel in this model will bring to us these new contributions. Now we have these new integrations, I2 and I3, okay? And these three integrations are basically integrations that we see usually in these models. For example, the first integration is the basic quantity from the free energy in the mean field approximation. The second is the equation, the integration we use to the gap equation. And the third integration is the integration we use to calculate the baryonic density. Then we have to follow here these basic conditions on the left. We have two new mass terms. So we have two equations to obtain with the principle of minimal sensitivity. And we have also the minimization of the effective potential with relation to the chiral condensate, which will bring us the better value, and the value that minimizes the potential of the chiral condensate. The thermodynamics we are interested is basically the pressure, the energy density, entropy, baryonic density, chiral density, sound velocity, and topological susceptibility. So we have to find a set of parameters to these two approaches in the mean field approximation and the OPT approximation. So here we choose something close to these two sets of approximations, okay? And let's try to see what happens when we calculate the effective quark masses and the phase diagram, okay? Here on the left we have the effective quark masses. In the first plot we have the masses as a function of the mu5 with the traditional regularization scheme. So it seems that the qualitative behavior is there, almost the same. If you look to the second plot, we have real big splitting between the large N approximation result with the OPT result, okay? So here we can see that at least at order delta we have already some difference. For the phase diagram, in the third plot, for the traditional regularization scheme we do not see any sensitive difference between these two approaches. But if you look to the optimized perturbation theory with the medium separation scheme, we have a splitting at low values of chiral chemical potential. So at least in the phase diagrams and for the effective quark masses, we do reproduce the results that we do expect from the lattice QCD and Dyson-Schwinger equations. Then we can look to the masses as a function of the quark chemical potential, okay? Here we can look first to the large N approximation. At some point we have these jumps that are indeed first order phase transitions, but when we apply the chemical potential, chiral chemical potential with the value 0.1 GeV, we have different jumps on this region, transition region. So when we apply the optimized perturbation theory, these jumps seems to be washed in some way. Then we can look to the baryonic density and the pressure, okay? Here we have basically the same idea. These two quantities have this, with the optimized perturbation theory, these values are lower when we compare with large N approximation, okay? I think it is indeed a big difference between these two approaches. And we can look to the equations of state, for example. If we look here, we can see that the chiral chemical potential shifts the values of the pressure, okay, as a function of the energy density to lower values. And the qualitative behavior is the same, but we have the splitting. And the last results are for the sound velocity, okay, which we have bigger values of the sound velocity as a function of the baryonic density with different values of chiral chemical potential. And the topological susceptibility, which shows us that fluctuations of topological charges maybe in this medium are being occur with lower values, okay? Well, the main idea here was to look what the optimized perturbation theory tells us about the phase diagram and some basic stuff from the thermodynamics. We take a look to some non-trivial effects on the first order phase transitions that happens as a function of the quark chemical potential. And also the topological susceptibility, for example, and the effective masses are underestimated in the beyond mean field approximation for this model. Well, this is all I have to say. Thank you very much.
Questions?
Thanks, William, for the talk. Can you go to the when you introduce a thermal cutoff?
Thermal cutoff?
Thermal cutoff. I didn't understand well what's the reason of the introduction of such a cutoff, because in principle this term can be integrated from 0 to infinity, so there's not has a
I agree with you. I agree with you. But depending on the choice of in which way you regulate this model in the thermal part, you can have different behaviors for different things. For example, if you are trying to look to the thermodynamics, if you integrate until some cutoff, okay, the chiral condensate can be negative at some point. But the thermodynamics, no, this is not true. If you integrate until the infinity, these thermal contributions, at some point you can have a negative chiral condensate, but you may have the Stefan-Boltzmann limit of the thermodynamics well behaved, okay? If you put this cutoff on the thermal contributions, your chiral condensate is never negative. So
you fix it in some point. It's temperature dependent also, or just another cutoff different from the?
It depends what you want to which thing you want to see. Here we integrate until the infinity, so we indeed did not look at these things, but at some point maybe the chiral condensate becomes negative at very high temperature.
Oh, okay. Thanks.
Hi. So I'd like to ask about the U1A breaking. So, so in this NGL setup, two-flavor NGL setup, the interaction is quite simple, but U1A breaking term is actually implemented. And so this NGL two-flavor, the U1A is explicitly broken. My question is, people usually think that the U1A breaking term should be suppressed at high density because the instanton is suppressed. But what do you think? So in this, the setup with chiral chemical potential, the U1A breaking is enhanced or suppressed? This is a very interesting question. Of course, this is not included in this calculation, but what do you think?
What I think about the behavior of the masses with high values of chiral chemical potential is that?
No. The usually people think that the instanton is impressed, the instanton excitation is suppressed by temperature effect or density effect, but mu5 induces a chiral imbalance. So maybe the instanton effect might be enhanced, or I don't know what happens. But so this is an interesting scenario that can be implemented in your calculation. This is just a comment.
Okay.
Thank you. I would like to come back to Christian's question about the cutoff. So there is still a mu5 dependent divergence in the vacuum thermodynamic potential, right?
If you...
There is, okay. So if you go one slide, so yeah.
Next slide.
So where you had these divergent integrals, there is one integral which still multiplies mu5 squared, something like that, no? The log is divergent.
Yes.
Okay.
Yes. The idea here is these contributions of mu5 get entangled, and at some point, if you are integrating until lambda, you are just putting away contributions for higher values of momenta.
So
but there, you can separate these things.
But then there is still a freedom there, no? Yeah, so that has a free constant parameter that you can change or tune, or what do you do with this parameter?
More questions?
Thank you. For your medium separation scheme, you said you could separate between many terms. Some of them were divergent in 2 slides, I believe. Yes, that's, the divergence integrals. Do you use the same regularization scheme for all of those terms?
Yes.
Or it's
Yes.
thought of? Okay. So have you thought of maybe using another regularization scheme to maybe, I don't know, make it simpler on some calculations? Or
It's a possible idea to apply, but it will be not good if the results change too much with the regularization scheme. So the idea here is just to separate the things and see what happens. And it seems that when we do not put away several contributions for higher momenta, so we can reproduce the Lattice result.
okay. Thank you.
More questions? If not, please, thanks, William, again.
Thank you very much for the opportunity. Okay, I'm going to talk you about the photon production in this rotating and thermalized medium, emulating a QGP. This research is in collaboration with Enrique Muñoz, and I'm going to start. I think that this is the, okay. Our starting point is the one-lobe photon-like polarization tensor. This object has been discussed in this conference many times in different contexts. And in particular, for a theoretical perspective, the exploration of new effects in this kind of diagrams comes from changing the boson-fermion couplings and the fermion propagator. For instance, I don't know, maybe in external magnetic field constant, as Villavicencio and other people talk about, or in a background with fluctuations, as Enriquez told you this morning. And for us, we're gonna take a fermion propagator in a vertical background, medium with angular velocity. And this propagator was originally derived by Ayala and collaborators. This is the paper where you can find it. And the propagator, I want to highlight two main features. The first one is that this propagator separates the spin projections of the fermions in the direction along and opposite to the angular velocity. You can find this in this way. I cannot see the red, so I don't know. And the other, okay, yes, it's a problem in my eyes, so I cannot see red. And the other feature is that this propagator in this approximation, the approximation is a rigid rotation in a cylinder. It just modifies the fermion energy. It's gonna be important later. Okay, with this in mind, we compute the photon production rate with this well-known expression, and we need to compute the retarded polarization tensor contracted with this metric. And this is the geometry that we are using with mid rapidity and all this stuff that we always do. And we can show that this object can be split into three integrals that I'm showing in the slides. The integrals can be done. Basically, the first one by parity, and another consideration is zero. It doesn't contribute. And in order to put temperature in this model, we use the Matsubara formalism as the thermal field theory do. So we do this, and I want to highlight this particularity of this expression, in which although the angular velocity defines a preferred direction in the space, it doesn't break the Lorentz symmetry in the sense of the momentums, spatial momentum is not separate. For instance, when we do calculations with a magnetic field, we always find a perpendicular momentum and a parallel momentum with respect the magnetic field direction. It doesn't happen here, and this is because in the propagator, the only modification is a shift in the energy. So we don't find this separation. What implies? It implies that the G remains angle independent in this geometry, and one of the conclusions is that the flow coefficients, if you want to compute it, are not affected by rotations in this approximation. I want to highlight that it's a rigid rotation and cylindrical one, maybe with other geometries, I don't know. Okay, with this in mind, we are now computing obviously flow coefficients, but the rates, well, okay, we compute with the usual tricks, mathematical tricks. We want to the imaginary part of these integrals, so we just take this part of the Dirac deltas. The integrals are easy to compute, and we can know that the vorticity enters as like a chemical potential, as we are discussing in this conference. Okay, we can compute this computationally. It's easy to do that, and those are part of the results. This is an ongoing work. So first of all, I want to know that we use this huge value of the vorticity just for comparison. Maybe there are not the physical ones. Maybe some words that say, okay, it might be allowed, but just for comparison. The first result, this is the photon rate for quark anti-quark annihilation. We sum over the two light quark flavors, and we can see the following. For small vorticities, small angular velocities, the photon production rate is almost the same that without vorticity. And if you increase the rotation of these systems, you can see that, okay, for large photon energies, they are almost the same, but for small photon energies, there are a kind of suppression of photon production, and this is given by a threshold in the photon production. This threshold is clearly in our expression given by these Heaviside functions, and the threshold is depending of the angular velocity of the medium, and of course of the mass of the parent particles that produce the photons. That's why in the next slide we compare the photon production rate for three different processes. The first one is electron positron annihilation, quark anti-quark, and muon anti-muon. And clearly we can see that the threshold moves depending of the mass, depending of the angular velocity, and there is suppression in the low energy regime. And in order to compare this shift of this threshold, we compare for zero vorticity, different values of the vorticity in terms of the mass, and again, the shift is clearly showing here. This is an ongoing project. The results are in construction, and basically this is what I want to tell you. Some other conclusions and future work. We want to relax this rigid rotation in order to have a more general geometry. The rigid rotation, maybe we can relax it in order to capture more realistic dynamics. And in this approximation, we can say if this cylinder rotates slow, there are photons in the low energy spectrum. If it rotates fast, the low energy spectrum is suppressed. This is all, and thank you for your attention.
Questions?
Who? Okay. Yes, this one, maybe this one. There is no suppression. Yes, the mass of this particle is much higher than these other two, and we believe that is because it dominates in the integral. The other terms are very small compared with the m squared that appears in the integrals. Yes, yes, yes.
A very, very simple question. I understand that this is an approximation for rotating liquids, so I'm wondering if you try to compare this with the results of Tuching and his collaborators, where they presumably calculated in the full angular momentum states and try to consider the complete spectrum.
We haven't compared with other works. Maybe I don't know what the reference is. Maybe we can talk if you give me, and I can compare. But we haven't done that. Thank you.
Yeah, thank you for the talk. The propagator is assumes because it's I know the propagator is a simplification that assumes something to get this simple form. Otherwise, it will be a complicated sum of Bessel functions. So,
Yes.
what's the restriction here in the vorticity to where you can apply this this kind of propagators? What are the restrictions you need, or which is the window for applicability of this propagator or this approach?
Maybe in the early stage of the QGP formation, I don't know, maybe the geometry is more cylindrical. I don't think that it applies in the medium stage or something like that. And that's why we want to modify the geometry. I don't know, maybe elliptical or spherical geometry. That's what I think.
But because it looks like it's, for example, the zero mode of the Bessel functions when you
Okay, that's a good point.
The full propagator, I mean, in this cylindrical motion.
I haven't think about it. Thank you.
More questions? There is one there.
So thanks for the nice talk. So I also want to ask about this propagators. So I think in the limit of small rotation, I guess this is equivalent to putting the fermion in a vertical fluid.
Yes.
In that case, we know from quantum kinetic theory, the dispersion relation is not shifted at first order in omega, but it looks like this is not the case for from your propagators.
No, it's not my propagator. It's the propagator of Ayala.
Alexander's
So ask him. I just take it.
Okay.
Yes. Actually, we did it again, the calculation with Ayala and Jorge. The calculation is, we think, well done. I don't know what to say in that comparison.
Offline,
Yes.
Thank you.
It's a point to take in account.
Question, comments? No? So please, thanks, speaker again.
Aquele tempo ali funciona também. Tá. Ali.
So the next speaker is Leticia Palhares. So she'll talk about testing infrared confining models beyond fundamental correlation functions. Please, Leticia.
Okay, thank you. So thank you everybody for being here, and thanks to Giorgio and Anna for the nice meeting and for letting me talk about my work. So I start apologizing because it will be only marginally related to the topics of the meeting. So my works that are more related to the presence of magnetic backgrounds have already been talked by other collaborators. So I'll take the opportunity of this talk to actually talk about something different, which I believe that maybe in the future could bring some interesting things in constructing effective models, better effective models in the gluon sector. So this is work, there is some background that is in collaboration with this group at the State University of Rio, where I'm from. Silvio Sorella, Márcio Capri, Marcelo Guimarães, and Bruno Mintz are the main the staff there. And what I'll be talking today in this specific talk will be actually the work of my former PhD advisor, Carlos Mena. And in the end, I will point out to the work of João Paulo, who actually talked on Friday. So the outline of my talk will actually be this. So I'll be talking about these confining models, and I want to enjoy the opportunity to talk to a different audience about this type of models. And I think that in the future we should maybe make a better effort in constructing models that also have more information about gluon dynamics, low energy effective QCD models that have more information about confinement and more information about gluon dynamics, and this might help when describing things in the presence of magnetic backgrounds, for example, rotation, as we have seen, and so on. And the type of framework I'll be talking about is the refined Gribov-Svanske scenario. So I'll give you a brief introduction to this and go through a little bit of the current status of this type of framework. And then I'll talk about some tests that can be made. And then here is my marginal connection to the theme of the workshop, because I'll be computing an anomalous magnetic moment of the proton. I won't be actually aiming at a very precise calculation of this quantity. I will actually be using this quantity as a test of these infrared models. And on Friday, you have the opportunity to see more about this type of models in the context of color superconductivity. That's the work of João Paulo, and he will talk on Friday. So my motivation to start with this type of models is actually the problem of confinement, which is, of course, very important whenever you're talking about QCD. And then I'll have to give my perspective of this problem and point to the direction that I would like to address. So in my opinion, I think in general grounds, it's very difficult to define confinement. I guess everybody in this audience knows this. Formally speaking, it's very difficult to define, but there are physical things that are very easy to understand. So we have a theory, Yang-Mills, or QCD, if you have quarks, that is given in terms of fundamental degrees of freedom, and these guys are not present in the spectrum of the theory. We have never observed them as asymptotic states. This is a statement of that has to be actually proven, right, that they are not present in the spectrum of the theory, but we have never seen them. And another side of this problem, so the confinement problem has two sides, is that these fundamental degrees of freedom, they build up a physical spectrum of bound states that is dynamically generated at low energy, and we do observe. And it's actually fantastic that you can start with a very simple Lagrangian with fundamental degrees of freedom, very few parameters, and get a whole spectrum of masses that's here hidden. So there is a plot of lattice results for the hadron spectrum, for example. It's quite kind of old, this plot, but you have much more results now. We know that lattice QCD reproduced the hadron spectrum with a lot of success. But my point is actually that, so for an interacting theory to have bound states, it's something not unexpected, right? So the real big issue about confinement is not the generation of bound states, it's actually the fact that the fundamental degrees of freedom are not in the spectrum. And this is something that, by large, we have no idea why this happens. We have no good answer for this. And this is something I would like to address. Of course, it's a very hard task, so it will be, it's not accomplished. But I would like to understand what happens to quarks and gluons in the infrared. So, of course, at some point we have to go to observables, and they lie on this side. But it's also very important to understand what happens to these guys. Why are they not present in the spectrum? What is the mechanism that drives this type of absence of the spectrum? And I think this is actually very important for phenomenology, because if we understand better what's going on with gluons, for example, in the infrared, maybe we would be able to construct better low energy models with dynamical gluons in it. So we would have a better handle of what's going on, for example, in low energy QCD model, low energy QCD transitions, when gluon dynamics is important. So this would be like the ultimate goal that we are not near there yet, but that would be the goal. So, and where do we start from? So depending on the audience, this can be very well known or not. But when you ask, you're doing quantum field theory, like we are doing particle physics, you want to address this type of quantum field theory, and you want to understand something about the fundamental degree of freedom, the first quantity you want to look at is the two-point correlation function, the propagator. In principle, this has information about what happens to the propagation of this degree of freedom. If there is a particle associated there, there will be a mass, there will be a residue, and so on. And if you look at the gluon, of course, if you're doing perturbation theory, the propagator of the gluon, the momentum function there will just be 1 over p squared, so it's just a function that goes to infinity when you go to zero momentum. But then we want to understand what happens at low energies, and we ask the help of our friends on the lattice. And in particular, this type of quantity, the gluon propagator, of course, I want to understand what's going on with the gluon, so I have to look at the gluon propagator. The gluon propagator is a gauge-dependent quantity, so I have to fix the gauge. But I can do this on the lattice. I can actually restrict to a few gauges, and the Landau is one that is very well studied on the lattice. So you do the normal gauge invariant simulations, generate configurations, and afterwards you restrict to a certain gauge. And then you can look at gauge-dependent quantities, for example, the momentum function in the Gluon propagator. This is an early result from 2008. And what people have seen there is actually that this quantity actually acquires a finite zero momentum limit. And this is kind of a mass generation, right? Because this is a mass scale being generated in infrared, and this has been confirmed by different lattice results. So we need very large lattices to have high precision in the deep infrared here. And for example, in 2019, you have this high precision result here, and you can see clearly that for very low momentum, you have a result that's finite. And this is also confirmed by other numerical, not lattice field theory, but other numerical approaches, semi-analytical, like the functional realization group, Dyson-Schwinger studies. Actually, there were some Dyson-Schwinger studies that appeared even before these lattice calculations that show this type of behavior. And there are different models that also have this type of behavior. So I would like to highlight the work done by the group in Uruguay and France, this Curti-Ferrari type of massive gluon models, even though it's hard to hear this type of massive gluon when you're talking about QCD. These are very successful, simple models that can reproduce a lot of things from lattice. Even phase transitions for SU2 and SU3, they get good results. So there are some reviews, and you can go there and look for this behavior. And this is all based on the fact that you're generating some type of gluon mass scale in the infrared. And there are also early results on gluon condensates that, of course, related to this type of thing. So here I will somehow try to describe this gluon propagator here in a scenario that will be the grid based on grid of copies, and then I'll try to go on from there to create something about gluon dynamics that is different from the usual standard thing. So what does this propagator has to do with the grid of problems? So I'll have to go back to the basics. So I'm trying to describe, so I'll just stay in Yang-Mills theory, but of course if you have quarks here, they don't play much of a role in this type of discussion. They will just be there as a determinant. And what you have here is the usual Faddeev-Popov description of the gauge path integral. So you have the gauge fields, the Gauss fields, and the Nakanishi field B here. And an important quantity that appears in this type of gauge fixings is the Faddeev-Popov operator. So what happens here is that if you integrate in these Gauss fields, actually what appears is a determinant of this quantity. And this is what you use to make any calculations in QCD or in electroic theory for in a perturbative setting. So the problem is that this is not completely right. And this was shown by Gribov in the 70s. You can actually show that this determinant of the Faddeev-Popov operator is actually exactly 0 in all cases, because you can show explicitly the solutions of gauge configurations that when you apply the Faddeev-Popov 2, you give 0 results. Those are gauge configurations that are normalized, are physical. So the determinant of this quantity is strictly 0. And this is a problem. So there is a new defined transformation of variables in the Faddeev-Popov procedure. And it seems like I'm crazy talking to you like this, because of course all perturbative results in LHC are based on this type of procedure. But the point is, whenever you are around the 0 field result, you do not reach this type of problem, and this type of description works. And the problem is exactly that I want to go to low energies. So I want to go to intermediate or lower energies and describe some gluon dynamics, so I cannot rely on this type of structure. So I have to make something about this formulation that actually avoids this grid of copies. And Gribov actually was the person who proposed the solution, at least partially, at the time. So he said, okay, if this determinant can be 0 at some point, I'll not integrate over all gauge fields. I will only integrate over gauge fields within a certain region where this determinant is greater than 0. And it turns out that this is a very well-defined quantity in certain gauges. In Landau gauge, for example, linear covariant gauge, you can define this region. You can show that it's closed, that it's convex, has all the nice properties. You can show that all the physics is inside this region. So you're not losing any physics in making this type of restriction. And actually now you have a well-defined integral that you can use beyond perturbation theory. So even when the gauge fields are large, or the coupling times the gauge field is large, so in the non-perturbative regime, you can still have a reasonable result. So the problem is that it's very hard to work with a restricted path integral, and took maybe around 10 to 20 years to get to a formulation that you can actually make calculations with. And Daniel Zwanziger was a very important person in getting there. And in the end, what he did was actually to transform that gauge path integral with a restriction to a certain region into a gauge path integral that you integrate over all configurations, but you get some constraints here in the form of a type of Lagrange multiplier, which is this gamma 4 that appears here. This gamma is actually a massive scale that is now non-perturbatively introduced in the Lagrangian in the end of your theory, in the action, but it's actually not independent, so it has to be determined by this gap equation for the solution of the Gribov problem to be implemented, at least partially. And the problem is that this quantity that you have to introduce here, the horizon condition, is something that depends on the gauge fields and on the inverse of the Faraday-Popov operator. And this is a very non-local quantity because it depends on the derivative of the covariant derivative. And you have an inverse of this. And Zwanziger was actually the person who proposed this, and also proposed the introduction of auxiliary fields that can put this in a local form. And in the end, you have a well-defined quantum field theory, local quantum field theory that you can work with and make calculations. And the story is not over, because once you introduce this type of restriction to the horizon, the Gribov horizon, actually the theory has some instabilities against the generation of dimension 2 condensates, and that's where more massive scales appear. So remember, now we are already in a fixed gauge, so it's not a problem to introduce other mass scales in the theory. And actually, right now, the status of this theory is that we have control of BRST symmetry. So after you fix the gauge, there is a remnant symmetry called BRST, and we can formulate a theory of BRST, modified BRST, that can control gauge dependence in the linear covariant gauge formulations like this. And this theory, these new condensates, in principle, they are not free parameters that you're adding. They are all dynamically generated within the theory. In principle, you have to compute an effective potential for them, minimize to get these values. And in the end, what you get is an action that should be describing gluons in an intermediate to low energy region, and where you have already from the start a background of massive parameters that introduce non-perturbative corrections. So you can actually show that solving the gap equation at one loop, for example, that the Gribov parameter is proportional to the exponential of -1 over the gauge coupling squared, and the same thing goes for the other mass parameters that will be actually proportional to the Gribov parameter. And okay, you have this theory, what can we do, what we have in the end, what's the status that we can do with this right now? So Zwanziger and the work of others afterwards has showed that you can get to a local and renormalizable action. So this is a predictive theory. So you can, in principle, get results in a self-consistent way, so you can compute everything within itself. Doesn't mean that you can do it, we have done it for all results. Actually, we have not done it fully yet because it's quite complicated, but in principle, you could do it. And one thing that is nice, in this, even though it's a low energy theory, you can interpolate directly to QCD or Young-Mills at high energies, because you're not modifying the ultraviolet. So all these new parameters are exponentially decaying in the ultraviolet, and you can show that the ultraviolet limit is exactly the same as Young-Mills or QCD. And you can show this, for example, computing the gap equation for this Gribov massive parameter at one loop. So of course it's an approximation, a one loop approximation, and you show this type of behavior, exponential -1 over the coupling, and you can actually rewrite this in terms of MS bar RG invariant scale that is present in the theory. Naturally, it's lambda QCD if you were in QCD, and you have this type of relation, and you can get actually numbers. You can show that in the ultraviolet region, this Gribov mass is actually very small, and it is exponentially suppressed if you go to the deep ultraviolet. So in principle, you are reproducing QCD at very high energies, but what about confinement, right? Because I'm talking about Gribov copies. Okay, this happens when there is non-perturbative physics there, but what could be the relation of this with confinement? So confinement is something very difficult to define. Nobody knows how to do it. Gluon confinement is even worse. We really don't know what gluon confinement is. But let me talk to you about something that could be related to this or could be just wrong, but maybe it could be related to this. So one thing that we know is actually, so if you go to, like in quantum field theory, you're trying to define an asymptotic state and understand if it is a well-defined asymptotic state. So in general, the propagator associated with a particle can be decomposed or written as an integral representation of a spectral function, right? And if this particle has a physical propagation, an asymptotic state well-defined, then this spectral function has interesting properties like being positive, being associated with a probability basically of propagation from one point to the other. And if you can actually define this function, this C of t, this Schrödinger function, is actually this type of integral of the spectral function. And this quantity is the sum of positive stuff. If the spectral function is always positive, this is the sum of positive things and should be positive. And this is actually a plot of lattice data. This is not refined Gribov-Swanziger. This is no model. This is a plot of SU3 Young-Mills theory, lattice data here for this C of t quantity, and this blue line is the 0. So you can see that lattice data for the gluon propagator, and this is also confirmed in other simulations, is that the gluon propagator violates this positivity of the spectral function. So even if we're not discussing these models, there's something very strange going on with the gluon spectral function. And this is called positivity violation. And this also happens in this type of RGZ model. So one thing that you could think, okay, the spectral function for the gluon is not standard. It means that it's not a propagating particle. So maybe this is a good news, right? Because we don't have asymptotic states of gluons. So maybe it's good news that you cannot define them if you consider the non-perturbative gluon propagator. So this is the way that we think that this theory could be consistent with gluon confinement, the fact that it's not present in the spectrum. So this is the reason why you can say that gluon is not present in the spectrum in this type of models, maybe from lattice data as well. So what happens in the RGZ, we also have this type of reflection positivity. I'm not showing you the C of t, but you could compute it. I'm actually showing you a lattice fit propagator of the 3-level expression for the RGZ propagator. And what you get in the end is a positivity violation, which is actually very explicit because the poles of this structure, which is complicated, are actually a pair of complex conjugated poles. So the mass poles for this gluon propagator, pair of mass complex conjugated poles. This is, of course, very non-standard. But on the other hand, the gluon here is not an asymptotic field, so maybe this could be good news. In any case, it's very hard to fit this type of function without complex conjugated poles. So there are few very strange forms for the gluon propagator that have been able to fit this form with good accuracy. So this is a big issue. Of course, if you only have lattice data points, it's very hard to judge what is the analytical form behind. So this is a big issue in infrared QCD community. But it seems to be that many approaches, Dyson-Stringer equations and so on, find this type of complex conjugated poles. And one thing that is my aim here also in the test I will be doing here is actually asking, can you actually get some physical phenomenology that is reasonable, that makes sense out of this non-trivial analytical structure for the gluon? And I think that yes. So actually you have not only results for propagators that actually usually fitted to lattice, but we also have results in RGZ for the ghost gluon vertex, and the tree gluon vertex is also underway. And everything seems to be in the same ballpark of lattice infrared results, even though it's just a one-loop calculation. And okay, could you construct physical spectrum out of these things so that you can go back to almost 10, 15 years ago that people have worked in this type of problems. So with a lot of approximations, you can actually estimate some global masses. So without quarks yet, they are compatible with available lattice data, and then you can go back to the details here with a few caveats about approximations. But in principle, there is some information about the spectrum there as well. And one thing that I would like to highlight, because of course I know it's hard to hear about gluon masses, is that this type of RGZ scenario actually has nowadays, since 10 years ago, or a little bit less than that, an exact modified BRST invariance that we have been able to establish, which means that we can control gauge parameter dependence within linear covariant gauges. So any gauge that interpolates between Feynman gauge and Landau gauge, we have the gauge parameter dependence under control. We have quantities that are gauge parameter independent that could be connected to physical things. And I'll not go into any details. So what's missing? A lot of things are missing, okay? So one thing is that it's quite hard to get quantitative predictions without fitting lattice data propagators in this type of scenario. So we have made a little bit of advance in computing the effective potential in this paper from 2019, but we have not been able to do that without fitting. So there is still one parameter that's being fitted in the end. So there is advance to be done in that direction, but it is in principle possible. It's very hard in this type of scenarios. Actually, in any non-perturbative scenario, it's very hard to discuss unitarity and physical operators. So this is something that we have to do. It's very hard to discuss quark confinement properties because all this physics is related to the Gluon sector. So this is also work to be done. It's very hard to discuss Minkowski space because the Gribov region is well defined in Euclidean space, but it's very hard to find a non-perturbative tool that works in Minkowski space, so very few other exceptions, but this is something that we have to do at some point. So what I'm going to show you here is that, okay, can we actually work with this to actually construct effective models and discuss phenomenology? So to do that, first of all, we're starting to make some tests with more physical things, observables, instead of only correlation functions. So up to now, everything I showed, except from the global masses here, were correlation functions of gauge-dependent stuff. So let's try to look at some phenomenology and see what we can get. So the first thing that I will actually show, and then the rest João Paulo will discuss more on Friday, is the anomalous magnetic moment that is related to the quark photon vortex. So this is actually related to the quark anomalous magnetic moment, but I'll discuss how to construct the proton anomalous magnetic moment in a moment. And this is the actual observable. So of course, the quark is confined, so you cannot directly observe the anomalous magnetic moment. But nevertheless, the quark anomalous magnetic moment is a gauge-independent quantity, so it's already a nice test. So this is also in principle accessible by lattice simulations, even though there are no results, only preliminary results. You can find the proceedings somewhere in the literature, but it seems to be very hard in terms of statistics to get good results for this, but it's in principle feasible for by lattice as well. So here I'll only be looking at this quantity. This is the photon, quark, anti-quark vertex, and you can decompose this like this, and you have two form factors, and so the first form factor is trivial, and I'll be looking at the second form factor in the deep infrared limit. So this is also interesting, the fact that this observable or this gauge-independent quantity is related to the deep infrared limit, because this is something that we like to probe with this type of theory. That's where it should make a difference, right, in the deep non-perturbative region. So how do we do that? So you do just a simple one-loop calculation, but I'm doing that in a theory where I have a modified Gluon propagator with all this background that I've showed you before. And here I'm using actually three different types of theories. So the Gribov-Zwanziger theory has this type of momentum function for the propagator. The refined Gribov-Zwanziger theory has more mass scales related to the condensates. And I'm also including here the simple massive Yukawa type propagator, which is the one used in Cauchy-Ferrari types of model that gives a lot of good results as well compared to lattice data. And here are the results. So if you just consider the massive Cauchy-Ferrari like or the Gribov-Zwanziger, you have sizable corrections to F2 function as a function of the mass of the theory. The typical mass that fits lattice data lies here around 400 to 500 in the Cauchy-Ferrari type of calculation. So you have sizable corrections to F2, and this seems to give a result that will be very different from you expect. Those are the results for the refined Gribov-Zwanziger scenario. Here you have more parameters, so you have more freedom to go around, but actually the values are fixed if you just want to fit lattice data, and here you have the values of the parameters that you can use, and the values for F2, so you have a factor of 2 respects to the perturbative result, the Schwinger one. And of course, if you want to really compare with some experiments, you have to construct the proton or the neutron anomalous magnetic moment. And for that, I'm just using a simple constituent quark model on top of this calculation. So I kind of have dressed quarks by these interactions. So this one gluon exchange with the confined gluon. And I will just build up the proton to estimate how it goes. So this is actually, if you go to a particle data group, this will be the state-of-the-art calculation of the proton anomalous magnetic moment that you find there, which is a bit funny. Even though it's extremely simple, it gets reasonable results. So I fix the proton mass to this value. And I have two things that I can tune, which is the dynamically generated gluon mass that I can actually fit lattice propagators. And there's one real unknown, which is the strong coupling constant in the deep infrared. And then in the end, you can get different results depending on the value of the coupling constant in infrared. So I'll show you here. But in principle, for any value of the coupling constant within a reasonable range, you can get the experimental result, which is the blue line here, depending on the twitching a little bit the value of the constituent quark mass, if you will. So all these models give reasonable results for the proton anomalous magnetic moment. Nothing weird appears, so it seems that the phenomenology can be well described. So the point is that this type of comparison is not very restricting to the model because we don't know a lot about what happens to the strong coupling in the infrared. And this is a compilation from 2016, but the situation is almost the same. This is not a plot, it's just a scatter of the values of the strong coupling that can be going from 0 to infinity, depending on the model that you're discussing. This is the value of the deep infrared limit of the strong coupling. This is how much we don't know what's going on. So there are many descriptions that actually the coupling goes to 0, the coupling goes to infinity, and the majority actually says that the coupling saturates at some point around 3 or 4 for alpha S. And this is something that we should try to understand more about. Of course, this is a scheme-dependent quantity, but within a certain model, it has a lot of information about the dynamics and about what's happening to the strong interactions in the non-perturbative region. And the other test of phenomenology, besides these anomalous magnetic moments, so you can go to the talk by João Paulo on Friday. He will be applying this type of models for color superconductivity. So it's always good to try to look at superconductivity because it's a physical type of system for which we have intuition. So nothing weird can appear and remain unnoticed. So it's interesting as a test ground for these complex conjugated poles that appear in this type of models. So and with that, I will not go into any details. João Paulo can talk about it later. With that, I just end my talk just reminding you that it seems that from lattice field theory, at least in Landau gauge, that there is some dynamical gluon mass generation or scale of mass generation in the infrared. Another point that should be important, at least for the students, that the Gribov problem exists in the non-perturbative regime of any Yang-Mills theory, and you should ask yourself whether this should play a role in what you're doing or not, because it is there. It's really, there's no way of going around it unless you really go through the work of do something, some gauge fixing, special gauge fixing like the RGZ scenario. And this is something that has been built upon. And maybe in the future, we can use this type of RGZ scenario as a gluon dynamics for an effective QCD low energy model. That would be the goal in the future. For now, we are testing it in some phenomenological context, and we don't see much problem in using them right now. And we hope that this remains so, and we can go to more interesting things in the future. So thank you.
Questions?
Sorry, but I mean, physically, sort of an experimentalist would define the magnetic moment of a particle in the deep infrared limit as you wait for the particle to process for a really long time in a magnetic field and you measure the frequency of precession.
Experimentally.
In principle, you cannot do that with a quark. I mean, there is
not with a quark. That's why I use the consistent quark model to
yeah, but then everything
the
depends on corrections and how you build up the proton out of quarks, right?
Yeah, that's true. But if you use the same consistent quark model and different models, maybe you can test the difference between these models, keeping the background fixed. And as I said, this is what appears in the particle data group as the status of the art for computing the proton magnetic moment. So it's not that bad. So it has some basic information in there at least. But it's true. It's not a good model. It's not a good model to compute the anomalous magnetic moment in the end.
More questions?
Thank you, Leticia. Beautiful talk. Can you go to the first transparency, please?
Yes.
You mentioned something about the Nakanishi field?
No, just that it's there.
So you handle the constant for fixing the gauge as a field now?
Yes, like this,
and
right?
Yeah, exactly. And the existence of Gribov copies depends on the fact that P is actually a field, or if you go to the Feynman gauge and put P equal set equal 1, for example. Because
So
I
if
never saw this. I asking
I
the
see.
existence of this functional integral over the B.
Okay.
Is something new
No,
for me.
this is just a way of introducing in the Lagrangian the fact that the divergence of A is 0. This is a standard procedure. You do this, even the Fadeev-Popov procedures, it's not related to the Gribov problem. But for Feynman gauge, for example, we do have a description of the Gribov-Zwanziger. Yeah, it won't appear in Feynman. It will be not there. And
It
so
will depend on that. Yeah, and second comment, many years ago, Gribov proposed a confinement theory basis on supercritical effects, appearance of complex poles because of some of these quarks went into the Dirac sea, and then in a very natural way appear a confining propagator for the quarks. Any comments about this old
for the
approach?
quarks? Oh,
For the quarks.
that work, I don't know. That's nice.
By the end of the
Gribov
70s.
has a lot of interesting proposals, but usually he did not develop them until you can really apply it in more advanced scenarios, but there are a lot of nice ideas. So this Gribov horizon, the absence of the pole in the Fadeev-Popov operator is actually related to Schwinger mechanism production of pairs of ghosts and things like that. But with quarks, I have never seen, but that's interesting.
This was related to supercritical effects in the context of the Dirac equation. Yeah.
Okay, nice. Thank you.
Okay, thank you. Sorry.
Questions, Kenji?
So I would like to ask you about the complex conjugated pole structure.
Yes.
So this is actually quite a problematic. For example, if you do the finite temperature loop calculation, then this is really a nightmare. But anyway, my question is that in the lattice community, the fit works quite well with Gribov Stingh form that probably you know. And that is actually the special case of your the propagator. That is instead of the complex conjugated pole, that you have actually degenerated the poles. Degenerate limit. That is in the denominator, you have actually squared form. That is called the Gribov Stingh form. And the lattice propagator is very nicely fitted.
This
so
is the proposal by Peter Loden, right? Yeah.
Yeah.
So the spectral function would be a derivative of a delta function. This is something very non-trivial as well. So we don't know how to treat this in a proper field theory context. But I know this is one of the proposals. It's the only other proposal that can actually fit the propagator.
Isn't it possible to have such a simplified denominator structure? That is a very special choice of special combination of the quadratic term and the zeroth order quadratic, and then so that you can get some squared form in the denominator, and then you can avoid such complex conjugated the structure. And I know for sure that the lattice data can be nicely fitted in such a special form.
If I don't know how many, but you need a lot of the sum of derivatives of delta functions. So derivative of a delta function will give you in the propagator the form of p squared plus m squared squared. So we have non-trivial residui. So we have a lot of parameters, and it's a very non-trivial structure. It's not only squared with one parameter. Okay, so and then you can get a nice fit as well. This is the only other form that we know. But this type of system, we don't know how to treat in the quantum field theory. So, for example, we don't know what type of interaction would be consistent with this type of spectral function. But this is a proposal by Peter Loden from Frankfurt, I guess. So it's possible. Oops.
More questions?
Nice talk, thanks.
Thank you.
Just a question about the confinement transition. In what is the news about the result of refining Griebel-Schwanziger in that case? Because as far as I know, there are some tries in different color group, like SU2 or SU3, are getting better and better, or?
So to compute the phase transition, what people do is to introduce a background field formalism, and in the background field you introduce a Polyakov loop coupled to the gluon field. So, and then you can actually compute some type of gluon potential from it. So the type of infrared model that has evolved more in that direction is the Cauchy-Ferrari one, so with the Yukawa type of gluon propagator. And they have done it for SU2, for SU3. They have very nice results for SU2 phase transition, SU3. For the Griebel-Schwanziger scenario, for RGZ actually, so there have been couplings in the background field with the Polyakov loop in the simplest formulation, so no center symmetry implemented and things like that. And you can get results, but the problem is that, let me show you, since you have the condensates, in principle you have to solve the gap equation, the two equations for the condensates, plus the minimization to get the condensates for the Polyakov loop, for example. So it's a four-dimensional extremization problem, and it's very hard to get a final result without fitting something at least. So in the end, you can fit the value of the critical temperature, but there's no prediction from a priori, you know. But you can fit the value, but it's not a prediction.
Are not strange at all.
No, it's not. It's not strange. You can get them, but it's a fitting of one value. So I don't know how much you can say it's nice. Okay.
So we are running out of time. Please, thanks, Leticia, again. So we have coffee break now, half an hour, and please come back to the discussion section.